let's do this. This is the two-body problem. You may have heard about the three-body problem. That's a different story. So the idea is I have two objects interacting with a central force. So there's a force that only pulls or pushes them apart. It could be a gravitational force. It could be a spring force, something like that. And I'm going to show you how to get that down to a one-dimensional problem. This is a classic thing that we do in classical mechanics, and there's a lot of stuff here. And I worked through this last night, so I had made some mistakes, and I might make some mistakes again, but we're just going to go through this together. And then after this, I'm going to make a video that does a numerical calculation of the two-body problem and shows that we get the same thing as this equivalent one-dimensional problem. So that's the key here, to get this down to an equivalent one-dimensional problem. Let's just get started. And yes, I have a whole bunch of paper here because it might take a while. Let me turn this camera off. That one. Okay, here we go. I think the mic's okay, so let's just start. So here I have two objects. I have mass 1, I have mass 2. And they have a position vector with respect to some origin, and who cares what that is. Now, how many degrees of freedom do I have? Well, if I think about this, R1 is x1, y1, z1 in Cartesian coordinates. R2 is x2, 2, y2, z2 in Cartesian coordinates. So, if I wanted to describe the situation, I would need to have 3 coordinates for mass 1, 3 coordinates mass 2, and if you add 3 plus 3, you get 6. So this is a 6 degree of freedom problem. There's no constraints because they're just out in space. So I have 6 degrees of freedom. So if I did the Lagrangian, and I'll link down below an introduction to the Lagrangian for you, that would be 6 Lagrangian equations. Don't want to do that. Okay, so instead, let's define the center of mass. So I want to define 2 things. I want to define this vector r. R is the vector from m1 to m2. So r equals, it's just a difference, right? It's going from 1 to 2, so it's r2 minus r1. That's important. I need my colors. Let's do it in green. Important equation. And then I'm going to define the center of mass of the system as, say, right there. And I'm going to use the vector capital R. And now we can choose our normal center of mass equation, which says that R is equal to m1 r1 plus m2 r2 as vectors all over m1 plus m2. And we can say that's equal to m1 r1, oh, my board shakes, plus m2 r2 all over capital M, where capital M is the total mass, and that's an important equation. I'm not going to highlight all the important equations, but these are the things that we're going to start with. So why do we even care? Well, we want to use the Lagrangian, and if you remember, the Lagrangian is T minus U, and I'm assuming that I'm going to have a potential, since it's a central force, that only depends on R, but I need to first get the kinetic energy T. So in Cartesian coordinates, I can say the kinetic energy is this. Okay, so let's go up here and say R1 dr1 dt is the velocity of 1, and that's going to be equal to x1 dot y1 dot z1 dot. Right, so now I'm using this notation here. You may not have seen this from my vector notation. This is the same thing as x1 I hat plus y1 j hat plus z1 k hat. This is just the ordered pair in angle brackets for matter and interactions. I just like it better that way. And then the other notation I'm using here is that x1 dot equals the derivative with respect to time of x1. So it's this dot notation. So if I take the derivative of this position, I get this vector, And now I want to find the kinetic energy. So the kinetic energy would be, let me just write it out in the full way. The kinetic energy of the system is going to be 1/2 m1 x1 dot squared plus y1 dot squared plus z1 dot squared. Right, because I'm going to need to find the magnitude of this vector, which I skipped, and then square it, because kinetic energy, T is 1/2 mv squared. So you have to find the magnitude of the velocity and then square it, because velocity is a vector. So when I take the magnitude, I get x1 dot squared plus y1 dot squared plus z1 dot squared. I take the square root, but then I square it, so I just get that. And then I have the other term is 1/2 m2 x2 dot squared plus y2 dot squared plus z2 dot squared. That's the kinetic energy. Okay, so let's rewrite this, because I don't want to deal with 6 coordinates. I want to deal with just 1. So let me rewrite this as T equals 1/2 m1 x1 dot squared plus 1/2 m2 x2 dot squared. That's the kinetic energy in the x direction. I know that seems really weird, but then I can do the same thing for the z, the y, and the z. 1/2 m1 y1 dot squared plus 1/2 m2 y2 dot squared plus 1/2 m1 z1 dot squared. Oh, the 1/2 should be in right here. Plus 1/2 m2 z2 dot squared. So I can treat the x, the y, and the z separately. I'm going to start with just the x. So if I start with just the x, then I have the following. X is the position from the vector, the component of the vector. Let me write it like this. R equals x, y, z. So x is going to be equal to x2 minus x1. And if you remember up here, that's just the same thing as this, right? This is the x component of this equation. And then I can write down the x component of the center of mass. So I can say Rx equals m1 x1 plus m2 x2 over the total mass. So I have those two equations. These are the x components of those equations. Okay. So now let's say, let me rewrite this equation. This is the part where I make a mistake sometimes. Rx equals m1 x1 over m plus m2 x2 over m. That's when I just write m without a subscript, that's a capital M. That's the total mass. Okay, where did I go from here? So I have, if I solve this for x2, I get x2 equals x plus x1. Now if I plug that in down here, I get Rx equals m1 x1 over m plus m2 over m x plus x1. All I do is substitute in x2. I put in this right here. So this gives me Rx equals m1 x1 over m plus that other term over here, which is going to be m2 x1 over m, and then I have plus this final term of m2 x over m. So I can factor out the x1, and I get x1 times m1 plus m2 over m plus m2 over mx. So now I get Rx equals, this is just x1 plus m2 over mx. Now I can solve this for x1 equals Rx minus m2 over mx. Very important equation. I'm going to put this in red. That's how important it is. And that's an x. And that's a terrible red. Oh man. Here's a better red. Let's see if that red works. Okay. Now what do? Now we need to do the same thing, except up here I solve for x2 and substituted it in. I want to do the same thing and solve for x1 and substitute it in. So if I do that, and I'm not sure if I even want to go through the whole thing. I hate taking shortcuts, but I'm going to leave this as an exercise for you. So I'm going to get x2 equals rx plus m1x over m. Also an important equation. Yeah, I'm happy with that. Okay, so now I have the position, the x position of the mass in terms of the location of the center mass and the vector from mass 1 to mass 2, and also for x2. And I need these because these are in the kinetic energy, but I want to get the kinetic energy in terms of r and x. So let's take the derivative of both sides, because I'm going to need x1 dot, right? That was in my kinetic energy. So that's a pretty easy derivative to take. x1 dot, the derivative with respect to time, is it's going to be rx dot minus m2 over m x dot. And then x2 dot is rx dot plus m1 x dot over m. This video is going to be long, so if you need some popcorn, go get your popcorn. If you need to take a stretch break, you know, I'll tell you when you can take that, but not now. We're gonna keep on working on this. So now I can put these into the x part of the kinetic energy. So T equals 1/2 m1 x1 dot squared, which is this. So I'm going to put rx dot minus m2 over m x dot squared plus 1/2 m2 times rx dot plus m1x over m dot squared. So this is x1 dot, that's x2 dot. Now I have to complete the square, so I have 1/2. I'm going to put the 1/2 out front. So I get, I'm going to do this in as short of a space as possible. m1 times r m1, and then I have this squared, so I get rx dot squared, and then I'm going to get two of these terms with an m1, so I get minus 2 m1 m2 over m x dot rx dot, and then I get m1 times this squared, so it's squared, so it's going to be positive, so I get m2 squared x dot squared over m squared. Now I need to do this term. I have the half all the way out over here, so I get m2 rx dot squared plus 2 m2 m1 squared over m squared. Remember, I have to square that. No, that's not squared. It's this times this. Two of those, yeah. So rx dot, and then I squared, plus m2 m1 squared over m squared x dot squared. So things are happening. This term cancels that term. Yay. Then I can combine. Here I have m1 rx dot squared. I have m2 rx dot squared. So let's combine those two terms. I get 1/2 m1 plus m2 rx dot squared. Now I can combine these other terms. I have this term and that term. So I get plus 1/2. Now I have, both terms have an m1 m2 over m squared, right? So this is going to be m1, yeah, m1 m2 over m squared. I factor that out. And then I have left, I have an m1 plus m2. And then I have x dot squared. Not dot, not just dot up here. That's just a typo. Yeah, that's it. So then m1 plus m2 is m, so this cancels with that. So I have 1/2 m, right, that's m, rx dot squared plus 1/2 m1 m2 over m x dot squared. And let's say mu is m1 m2 over m, reduced mass. So I can write this as t, the x part is going to be 1/2 m rx dot squared, that's a scalar value, plus 1/2 mu x dot squared. Check that out. So this says that the kinetic energy in just the x component, I haven't done the other parts yet, the x component, the x part, if I separate that out, which is not a component because it's not a vector, is equal to the kinetic energy of the center of mass plus the kinetic energy of this reduced mass. So this is like the motion relative to the center of mass. But we don't use we don't use one of the masses. We use the distance from one mass to the other and then this reduced mass. Now I could redo the same thing for the x and the y and I should get the exact same thing, right? It's the same math. I'm just using x's and y's. So that means I actually get this. If I put that all together, I get t equals, changing my page, my notes. I actually do have notes because I don't want to make the same mistake I made before. So I say t equals 1/2 m rx dot squared plus 1/2 m ry dot squared plus 1/2 m rz dot squared. And then the other term is plus 1/2 mu x dot squared plus 1/2 mu y dot squared plus 1/2 mu z dot squared. That's my whole thing. Now I can factor this out and I get 1/2. Let's call that, this is notation here. Let r dot squared, that's the magnitude of the total vector, is going to be equal to rx dot squared plus ry dot squared plus rz dot squared. And then r dot squared would be x dot squared plus y dot squared plus z dot squared. So I get t equals 1/2 m r dot squared plus 1/2 mu r dot squared. So the motion of the center mass is the kinetic energy of the center mass, and this is the relative to the center of mass. Now let's write the Lagrangian. L equals 1/2 m r dot squared, it's a vector, squared, not two dots, plus 1/2 mu r dot squared minus u of r. I don't know what that is. Okay, but I'm saying the potential, since it's a central force problem, the potential only depends on the magnitude of the distance between the two objects. So now if I use Lagrangian, I have two variables. I have big R and little r. They're actually 6. Okay, because this is a vector. But let's just treat that as the magnitude. And if I say, what about the partial of L? I mean, I could do the R. Let's do just the R, X component. Partial. So this is the Lagrangian. Partial of L with respect to Qi equals d dt. Partial of L with respect to Qi dot. This is the Euler-Lagrange equation that solves the equation of motion. So Q would be some variable, and this would be the derivative of that variable. So if I do that for Rx, I get the partial of L with respect to Rx, which would be what? There's no Rx in here, so that's 0. So that's going to be equal to the derivative of partial of L with respect to Rx dot. So the partial of Lx dot would be, this would be the derivative with respect to time. If I take the partial of Rx, I could do it up here, I get 2m rx dot. No, I get m rx dot. And the derivative of that has to be 0, which means that rx dot equals 0. Right, because the derivative of this has to be 0. No, it's a constant. So really, if the velocity is constant of the center of mass, then it's really kind of a boring part of the problem, right? So we really don't even have to worry about that. We can pick, let's pick that Rx and Ry dot and Rz dot are all 0. And let's even do this. Let's say that R dot equals the vector 0 and R equals 0. Let's put the origin at the center mass. Let's just make things easier because we're trying to get this down to an equivalent one-dimensional problem, so why make it more complicated than it needs to be? So now we have our situation like this. I'm going to draw it quite simply. Here's mass 1, here's mass 2, here's the center of mass, which is at the origin, and so this would be R, and this would be R1, and this would be R2. So now I get the following versions of my equations, which I had back up here. So now Rx is 0 in these two equations, so I get x1 equals negative m2x over capital M, x2 equals m1x over capital M. So now I can find, I only need this, and these are, I do the same thing for x, y, and z. I only need to know the displacement from one object to the other. It doesn't really matter about, I mean, I've assumed the center mass is at the center. Okay, so now let's look at, so we've gotten this down from 6 to 3. That's what we've done so far. We were at 6 degrees of freedom, now we have 3, because there's a center mass at the origin. It doesn't move. We can assume it doesn't move. If it does move, it's easy to compensate for that at the end. But right now we're down to 3 degrees. So we've made the problem half as easy, half as complicated. Not half as easy. But now we need to simplify it some more. So now we're going to start looking at angular momentum. And there is a problem here. What symbol do you use for angular momentum? Yes, L. And we already used L for the Lagrangian. So I'm going to switch back and forth between these two L's, but I'm going to be explicitly clear so that we won't make mistakes. So this is the angular momentum. The angular momentum about the center mass is going to be defined as L equals R1 cross P1 plus R2 cross P2. That's the definition of angular momentum, where P1 is M1 R1 dot. Right, that the momentum is mass times velocity. And P2 is M2 R2 dot. So if I put that in up here, I get L, the vector, is equal to M1 R1 cross R1 dot plus M2 R2 cross R2 dot vector. Now I want to get this in terms of other coordinates. So let's just say this. Let's say that R1 is negative M2 over MR. And I can get that from up here, right, if I do the same thing for the x and y and z. And also R2 is M1, not R, R over M. Now I can take the derivatives, because I need the derivatives. I want to put that stuff in here. So the derivatives of these are pretty easy, right? I can say R1 dot is going to be negative M2 over M R dot, because that's just a constant. And then R2 dot is equal to M1 R dot over M. Am I still recording? Yeah, cool. Now I can put these into this formula up here and for the R1, R1, R2, R1, R1 dot, R2, R2 dot. Now I get the angular momentum is L is M1. And now instead of R1, I'm going to get negative M2 over R. I'm sorry, negative M2 over R. Negative M2 over MR. Oh gosh, just negative M2 over MR cross. Now I got to put in R1 dot, which is equal to negative M2 over MR dot. Now I can do the same thing for the other mass, plus M2. And now I'm going to get this same term twice, right? So I'm just going to factor that out. So I get M2 M1 squared over M squared R cross R dot. So this is going to be equal to M1 M2 squared over M R cross R dot plus M2 M1 squared. Oh, that's a squared down here too. M squared R cross R dot. And then you can factor out the R dot, right? So I get, that's a plus. I get this is equal to M1, M2. They both have an M1, M2, but they have an extra term in there, over M squared. And then I have a leftover M2 plus M1. And then I have R cross R dot. And this is equal to, oh, look, that cancels. Now I have M1, M2 over M. What? That's the reduced mass. R cross R dot, or equal to R cross mu R dot. So this says that the angular momentum is like there's only one particle moving. And it's a particle that has a position value of R, which is the vector from the two. Actually, we're here at the origin. So that's my R. It's that distance. And it has a mass of mu. So the angular momentum is like the angular momentum of one particle. Now, if the angular momentum is constant, which it is because here's the angular momentum principle, torque net, the vector is dl dt, and there's no torque on the system because there's no external forces, this is 0. So L equals a constant. Now, if L is equal to a constant, then I can define, let's say this, R equals x, y, z. R dot, actually, let's pick this. I'm going to pick this to be 0, and R dot to also be x dot, y dot, 0. Then the angular momentum will be 0, 0, LZ. If I do the cross product between these two vectors that don't have a z component, the answer is in the z direction. This is important because this means that if I confine my system into the xy plane, then it will have a constant angular momentum in the z direction. No matter what situation I have, I can always pick a plane to define the system in. There's only two objects. They're going to be moving in a plane. I can pick whatever plane that is. And I'm going to pick x, y, and z. I mean the xy plane. So that means I can change my coordinate system. So now here's x, here's y, and it's as though I only have one particle. All I care about is r, right? So here's r, here's my particle, reduced mass mu, angle theta. Now that's this is the polar coordinate r. And now I can get the kinetic energy in terms of these coordinates. So let's say x equals r cosine theta, right? Because that's just this triangle. This is x. That's y. Y equals r sine theta. Now I want to get the kinetic energy in terms of r and theta. and r dot and theta dot. So that means I have to say T is 1/2 mu x dot squared plus y dot squared. I know that's true in the Cartesian coordinates, but now I've got to find x dot and y dot. So let's say x dot, the derivative of x, is going to be the derivative of r with respect to time, which is r dot. But now I have to take the derivative of this. The derivative of cosine theta is negative sine theta. But then I have to take the derivative of the inside, so I get a theta dot. Now let's do the same thing for y. Y dot is going to be r dot sine theta plus r cosine theta, theta dot. Now I need to square them. So x dot squared is going to be r dot squared cosine squared theta minus 2r sine theta, theta dot, cosine theta, plus r squared sine squared theta dot squared. Y dot squared is going to be r dot squared sine. I never gave you a break, right? We may have done this before. If you need to run to the bathroom, I'll keep going, and you should be okay. Sine theta squared, and then I have two of those terms, plus 2r sine theta, theta dot, cosine theta. I switched the terms so it looks like that one, plus r squared sine squared, cosine theta, theta dot squared. So when I add these two terms together, x squared plus y squared, that term cancels that term. I have r dot squared cosine squared theta, r dot squared sine squared theta. The cosine squared sine squared factors out, and I get, which is 1. So I get T is 1/2 mu r dot squared. And then this term over here, I have, again, the sine squared cosine squared factor out, and I get plus r squared theta dot squared. And that's my kinetic energy. Cool? Okay, now let's write down the Lagrangian. L equals 1/2 mu r dot squared. And remember, this is not angular momentum, that's Lagrangian. This is not the vector r, this is the polar coordinate r. Plus r squared theta dot squared minus u of r. I don't even know what u is. It's just some potential. Okay, we're good. This may be my longest video, but I'm having fun. Oops, I turned that on. Hi. Okay. Let's see. So now let's do the Lagrangian for theta. We have two variables, theta and r. I should rewrite that. I'm going to run out of paper. That's exciting that I went through that much paper. It does take, I use a bigger pen, so it takes up more space. So let's just say the partial of L with respect to theta is equal to 0. Why? Well, show me where you see a theta. There's no theta in the potential. We said that can't be true. There's no theta in the kinetic energy, so that's 0. So that means that the derivative with respect to time of the partial of L with respect to theta dot is equal to 0. The partial of L with respect to theta dot, well, there's only one term with theta dot in there. It's right here. So I get 1/2 mu r squared, and then I bring the 2 down. It's going to cancel with the 1/2, and I get mu r squared theta dot. And that has to be equal to a constant. And let's choose that constant to be L. We pick that constant. But that is a constant because there is no theta term in the potential energy. That's why that's there. Now let's do R. So the partial of L with respect to R, and I'm not going to pull it up. We can do it. It's just going to, well, I guess I should. So there's only, this term has an R and that term has an R. Okay, we don't know this function, but we can still take the partial. So the partial of this with respect to R is going to be mu r theta dot squared. So I get mu r theta dot squared minus the partial with respect to R of u of r. Now, what about the partial of L with respect to r dot? Well, there's only one term with an r dot, and it's this. So I get mu r dot. Now I need to take the derivative of that with respect to time, and I get mu r double dot. So this is equal to this. So I get mu r double dot equals mu r theta dot squared minus the partial with respect to r of u of r, which we don't know what that is, but that's fine. So this is pretty legitimate. It has a black box around it. So we can think about this as mass times acceleration in the r direction. If that's the case, then this would be the real force, and this would be a fake force, right? This is the force that makes it act like it's in a circle. Does that make sense? So, and in fact, we can even solve for theta dot. Up here, I can say theta dot equals L over mu r squared, because I already said that. And now, if I put that in down here, I get mu r double dot equals mu r L squared over mu squared r to the fourth minus partial with respect to r u of r equals, now we can just cancel some stuff. I get L squared over, where did I get the 2? Oh no, that's right. L squared over mu r cubed minus the partial of u with respect to r. We're done. We're technically done, right? We're done because now I have a one-dimensional differential equation with respect to r double dot r and then this potential, which only depends on r. So I've gone from a 6 to a 3 to a 2 by using the angular momentum, and then 2 to 1 by saying angular momentum by using the Lagrangian. Now, one way to think about this is, think about this. This is my total force. So I have a force due to the potential, okay? And then I have this fictional force due to, I'll call it F, it technically be the centrifugal force. And I will link down below a video on the difference between centripetal and centrifugal force, just because it's fun. I might forget, but if I do, just let me know in the comments. So the centrifugal force is equal to this, L squared over mu r cubed. How would I find an effective potential? I could say, well, if I can find the potential, the centrifugal potential, let's call it, it's going to be negative the integral of FFC dr. So if I integrate this with respect to dr, I get 1/2 L squared over mu r squared. And that's my rotational potential. So if I want to treat this as a particle in a well, which I'm going to do, then it has this potential plus the real potential. And that gives me the total effective potential. Now, I want to plot all that stuff. And I want to make a comparison between that and the real, a numerical calculation for two orbiting bodies. But I don't want to do that here because this is a long enough video and I need a break and you need a break. And that's the only reason. So I'll stop right here. We did do it. This was the key right here. And I'm gonna do this in another video and show you how the two things relate. And I've had fun. I don't know if you've had fun, but I've had fun. So thanks for sticking with it. And I will talk to you guys later.